Hi everyone, let's discuss UV visible spectroscopy. Most organic molecules and functional groups are transparent in the portion of the electromagnetic spectrum, which we call the UV and visible regions. That is, the regions where wavelengths ranges from 190 nanometer to 800 nanometer. So that this spectroscopy is of limited utility. Yet, some cases we can derive useful information from these regions of the spectra, and when these information combined with the detail provided by the IR or NMR spectroscopy, we can lead to valuable structural proposals. When continuous UV visible radiation passes through a transparent material, a portion of the radiation may be absorbed. If that occurs, the residual radiation yields a spectrum with gaps in it, and it is called an absorption spectrum. As a result of energy absorption, atoms or molecules pass from a state of low energy state, that is ground state, to a state of higher energy, that is excited state. The energy differences between these levels in most molecules vary from 125 to 650 kJ per mole. Here, the molecule absorbs the electromagnetic radiation in the UV and visible region, and it results in the transition between the electronic energy levels. As a molecule absorbs energy, an electron is promoted from an occupied orbital to an unoccupied orbital. Generally, the transition is from the highest occupied molecular orbital, that is HOMO, to the LUMO, that is lowest unoccupied molecular orbital. In order to observe a transition, the electromagnetic radiation that gets absorbed should have an energy which is equal to the energy difference between the excited and ground state. That is, if h nu amount of energy is getting incident on the molecule, the energy difference between the molecules should be equal to h nu. If so, the transition happens. There are various molecular orbitals found in a molecule, including sigma, pi, n, pi star, and sigma star. And the transitions can happen from sigma to pi star, sigma to sigma star, pi to pi star, and n to pi star, and finally n to sigma star. For most molecules, the lowest energy occupied molecular orbitals are sigma orbitals, which corresponds to sigma bonds. The pi orbitals lie at somewhat higher energy levels, and the orbitals that hold unshared pairs of electrons is called n orbitals or non-bonding orbitals, and they lie at even higher energies. The unoccupied or anti-bonding orbitals, that is pi star and sigma star, are the orbitals of higher energy. That is, sigma and pi constitutes the bonding molecular orbitals, the n molecular orbital represents the non-bonding molecular orbitals, and pi star and sigma star together constitutes the anti-bonding molecular orbitals. All of the transitions that at first sight appear possible are not observed. Certain restrictions called selection rules must be considered. One important selection rule states that transitions that involve a change in the spin quantum number of an electron during the transitions are not allowed to take place. They are called forbidden transitions. Let me tell you the principle of this absorption spectroscopy. If there are greater number of molecules which are capable of absorbing light of a given wavelength, the greater the extent of light absorption. Furthermore, we can say the more effectively a molecule absorbs light, the greater the extent of light absorption. From these ideas, we can formulate an empirical expression known as Beer-Lambert law. And it is expressed as absorbance A is equal to log I0 by I, which is equal to epsilon into C into L. If the UV visible radiation falls on a molecule, it may get absorbed by the molecules, or there will be a scattering loss, or there will be a losses of reflection and by interference. And after all this process, the radiation will emerge out of the molecule with lower intensity. A higher intensity of radiation get entered and a lower intensity radiation emerged out. That means the molecule should have absorbed some energy. That absorbance is calculated by this Beer-Lambert law, which is given by absorbance A is equal to log I0 by I, where I0 is the intensity of the light incident upon the cell and I is the intensity of the light leaving the cell, and which is equal to epsilon into C into L, where epsilon represents the molar absorptivity and C is the molar concentration of the solute and L is the length of the sample cell that we have taken, which is in centimeters. The remaining things related to UV visible spectroscopy we will discuss in our next session. Thank you.